Hello, ladies and gentlemen. This is Mr. Hunter, and this is your Newton's Laws Notes Part 1. So just to give you a heads up, this unit I'll be doing grading a little differently, and that we're going to actually be working on standards. And so in your grade book, you're going to start seeing like standard 1 might be Newton's laws, and you're going to see like a grade with Newton's laws concerning some of the things that we're doing. So as I stated in class, we have left kinematics, which kinematics is the study of how things move, and we're entering into dynamics is, okay, we've studied how things move, now we're looking at why do things move the way they do. And Sir Isaac Newton did the fundamental groundwork for understanding how things move the way they do. And so as we talked in class, things move because of forces. Forces are push or pull, and there's different types of forces. So from these forces, he actually came up with 3 laws that kind of govern all motion of objects. And his first law is a law you guys have heard about before, and you can usually state it, but it says an object at rest, so an object at rest will stay at rest, and then an object in constant, I can spell, I swear, constant straight, apparently I cannot spell, straight line speed will stay that way if all forces are balanced. So Newton's first law says 2 things. It says, whoops, I'm moving the whole page. An object at rest will stay at rest, and an object in constant straight line speed will stay in constant straight line speed. So an object at rest will stay at rest. An object in constant straight line speed will stay that way if all forces are balanced. So that is Newton's first law. An object at rest will stay at rest, and an object in constant straight line speed will stay that way if all forces are balanced. This is also called the law of inertia. Law of inertia. So, you guys often has heard an object that is moving will keep moving, and an object that's at rest will stay at rest if all the forces are balanced, which is true, but remember when we talk about motion, we have to talk about constant straight line speed. So, which brings us to inertia. Inertia is resistance to change. It's like old people, they don't like change. So, it is resistance to change. Okay, that's not entirely true. There are old people who like change, but it's just a stereotype that I'm using for. So, inertia is resistance to change. It is proportional to mass. And mass is measured in kilograms. So inertia is proportional to mass. Mass is measured in kilograms. So the more mass I have, the more inertia I have. And as we've learned, if you have mass, you have gravity. So the more massive you are, the more attractive you are. But that also means that you have more inertia, because inertia, as Bill Nye says, is a property of matter. Because the more inertia you have, the more resistance you are to change. For example, if I were to face a linebacker who is twice my weight, he's going to have twice the inertia that I would have to change, and that would be his resistance to change. So I need to change his direction to get out of my way, and I would have to put in like twice the effort to do so. So the question that I then have is, well, what is an unbalanced force? If you think about the word unbalanced, Un means not, balanced means equal. So it's an unbalanced force, or it is a not equal force. And we call this in physics force net. So an unbalanced force is an unequal or not equal force, and we call that in physics not equal. So when Fox equal, thank you, smartboard. Anyways, I'll just undo that. So an unbalanced force is a not equal force. So when I'm playing like tug of war, am I recording any of this? When I'm playing tug of war, yeah, there you go. Okay. I'm sorry about that. So when I'm playing tug of war, an unequal force would yield me or someone else winning. If our forces are balanced, we're either doing two things. We're not moving, or we're moving at a constant linear velocity. So if I'm applying under Newton's first law and my forces are balanced, which means they're equal on all sides, then I'm either not moving. Like if you're sitting in your chair right now watching this video, your forces are balanced. You are moving at 0 meters per second. Or I could be driving down a street and moving at a constant speed. My forces are balanced. Now, here's what we're going to do. We're going to draw something called a free body diagram. A free body diagram is just a vector representation of the forces, or whatever vectors you have. So all it is vectors. It's a vector representation. It's just arrows. So for example, in example 1, the object is at rest. Well, if it's at rest, what are the forces acting on it? Well, I have the force of gravity pulling down. And remember, force of gravity is going to be mass times acceleration due to gravity, and it also equals your weight. So when they're saying, hey, what's the weight of the student, they're talking about force due to gravity. Just like I said in class, ladies and gentlemen, star that. Know that, because it comes up so much, and every single year it comes up and students still get it wrong. Force of gravity equals your weight, and to figure out your weight, it's your mass times acceleration due to gravity. Just like we took notes in class. Mass is the amount of matter you have. Weight is your mass affected by gravity. So since this box is at rest, the forces have to be equal, but opposite. So then we have a force, like you sitting in your chair right now. You have the force of gravity pulling you down, and you have the chair pushing you up. This chair force is called force normal. It's force normal, and normal means 90 degrees. So it's the force perpendicular to the surface. It's 90 degrees. So now, I was supposed to draw that right here. Whoops, I drew it on the previous one. So I have force of gravity. My bad. And then force normal. Notice that they are equal. And because they are equal, I can actually say, hey, my force normal equals my force due to gravity equals my mass times acceleration due to gravity. Now, I put the G signifying gravity. It also, you could say Y. It's the same thing. It's at 9.8 meters per second squared. So, because they're equal and opposite, oh, my bad. Actually, it's technically this, right? Because they're equal in opposite directions. Okay, flip over to the back, and we're almost done. So example 2, an object moving at constant linear velocity. So let's say its velocity is moving to the right at 3 meters per second, but the forces are balanced. So let's say like this is 10 newtons, and this is 10 newtons. Now think about it. This would be negative 10 newtons. That would be positive 10 newtons because they're heading in opposite directions. And then I still have gravity pulling down equal to the force of the table in this case, pushing up, both equal and opposite. So that's force normal, that's force of gravity. My recommendation with these notes is once you take them down, you should also at some point recopy them over. You should make sure you're understanding what's going on in these notes. So the question is, does the velocity change? Well, according to Newton's first law, all the forces are balanced. There's 4 forces acting on these boxes, and they're all balanced. So no, the velocity doesn't change because all forces are balanced. And how am I doing on time? Oh, I'm over. Okay, and then lastly, we already drew the free body diagram of forces acting on the box, so we are done. This is due Friday. I look forward to seeing you guys because we're going to start applying these concepts in class, and it's pretty fun. I'll tell you about it in class. See you then.